We're going to take a look at a physical property that you're probably aware of, but it's our first quantitative one, and that's density. And this little graphic here is something I want you to be able to explain to me at the end of the section on density, why I chose this. So you're going to be able to explain the difference between mass and density, both with numbers and in plain English, and some of its implications. In metric, there are only a few fundamental units, just 7 of them, for distance, mass, time, temperature, electric current, light intensity, and amount of substance. We call metric MKS for meters, kilograms, and seconds. Temperature is in Kelvin, not in Celsius. They're equivalent to each other, and we've already done amperes. So it's only candela and moles left to go. Everything else is assembled from these. There are hundreds of units, but they all come from these 7. So for example, speed is distance over time. Area is distance times distance. So you construct these. Amperes, you learn itself is actually a constructed unit, but it's considered to be fundamental for really complicated reasons. So we have area, volume, speed, energy in joules is actually a kilogram meter squared per second squared, which is why we gave it the nickname joule. And all the electrical terms we've used are actually combinations of the other ones. And so the triple equal sign is what we use to show that things are identically the same. So 1 joule is identical to a kilogram meter squared per second squared. The derived units become really important later in chemistry and physics. Our first derived unit is fluffiness, density. It's a measure of how compact or fluffy something is. And I would like you to use the term fluffy and squishy, right? So you convince me you know which way you're talking about. So density is equal to mass divided by volume. Something that is fluffy does not have a lot of particles in the same amount of size. Okay, so this is fluffy, this is just right, and that's too squishy. The formula is meaningless if you don't understand it. So this formula has meaning. The mass is basically a count of the atoms in a way. It's telling you how much matter there is. And that amount of matter has nothing to do with gravity. I'll give you an example. If you had 2 golf ball sized objects, one of them was literally a ping pong ball, and the other one was solid lead, and they were both painted white. Do you actually think if you went on the space station and someone whipped the lead ball at your head, that it would not hurt because there's no gravity? Would you expect it just to bounce off going, wow, it's weightless now? No, the matter is still there. The atoms are there. So we take the total amount of atomic particles, the mass, and we divide it by the space they occupy, the volume, and then we get a measure of squishiness or fluffiness called a gram per cubic centimeter. And I want you to think of it as gram for every cubic centimeter. And a cubic centimeter is about the size of a sugar cube. So how much would a sugar cube sized piece weigh? So we do not measure density with a densityometer. We calculate it from 2 other units using this formula. We standardize it to 1 cubic centimeter, sometimes a cubic meter, sometimes a cubic kilometer. But basically, if I gave you an object, we're just cutting off 1 little tiny cube of it and getting that mass of a sugar cube sized piece. Grams for every cubic centimeter. Now, most of you know how to do basic volumes. You probably can do at least 2 of these. You might be able to do all 5 at this point. Which ones do I want you to be able to use? Just the cubic shapes. If you want to do cylinders and spheres, that's advanced work, right? And volumes can also be used with measuring cups. And this is very convenient for liquids. In metric, a milliliter is the liquid measure and the cubic centimeter is the solid one. Fortunately, they're the same thing. So 1 milliliter and 1 cubic centimeter are exactly the same thing. There's no difference between them. When we're going to take the measurement, you can use a balance for the mass and a graduated cylinder for liquids. If they're solids, you're going to need a ruler to actually measure them. And you will choose the graduated cylinder that best suits the role. The smaller, the better. You get more precision. A great advantage of science over math is that many calculations mean something, and you can make common sense of the answer. And if your math is in error, you can often realize this because the answer makes no sense. For example, if a math teacher gives you 17 times 12 and you write 194, this is wrong, but you can't see it at the time because there's nothing to think about. But if you do this, bananas are $4 for 12. How much is one banana? And for some reason, you decide the answer is achieved by multiplication. And you go $4 times 12 equals $48 for a banana. This answer is ludicrous. $48 for one banana? Even in COVID-19 ripoff scams, nobody's charging $48 for a single banana. Yet. So you suddenly go, oh, wait a minute, I multiplied. Dividing makes more sense. There's just no freaking way. If $4 for 12 bananas, like, it's then, and you realize it's going to, well, what if I did 12 divided by 4? That'd give me $3 a banana. But it's 4, no, it's 4 divided by 12, and that's 1/3 of a dollar. Yeah, that works out. You know what I mean? You can think your way to the answer. So density has this capability as well. Now, you don't need to watch my video on using a triple beam balance. We're seriously not going to be using them unless we get back to school. But I do want you to watch these. Now, you may not be able to click on the links here. I'll try to add them to the video description. We'll see. If not, go into my slideshow and watch these. They're really cool. Trust me. It will help you grasp the concept and see how it relates to the real world. Don't just skip them. Please watch these 5 videos. And number 6 is a mystery. Did I make a link for number 6? Is it invisible or is it not there? So we're going to pause now, and then I'm going to start going into some examples for your density assignment. Welcome back, my fine young schmetterlings. We're going to do a few examples with density together. Quantifiable physical property.
Lorraine, my density has brought me to you.
What?
Oh, what I meant to say was...
Wait a minute. Don't I know you from somewhere?
Yes, I'm George McFly. I'm your density. I mean, your destiny.
Alrighty, so we've already looked at this formula. Density, or the fluffiness of something, is mass over volume. The mass is kind of related to the number of atoms and how they're arranged, and we'll see that a little bit later. And the volume is the space it occupies. Okay? It is a derived unit, grams per centimeter cubed. It's not a fundamental unit. It's made up out of 2 others, just like kilometers per hour is made up of 2 different kinds of unit. Now, I like to use the Greek letter rho. Row your boat. It looks like what you see there. It looks like the letter P, and it's the Greek letter rho. Is also commonly used for density. Why can't I use D? Because if you look it up online, you're going to see rho used all the time. By the end of my course, the blue Greek letters will have looked at. Though I goofed here. Not chi and psi. We won't do those. Just omega. So alpha, beta, gamma, delta, epsilon I'm going to use. And pi, you already know that I'm going to add rho and sigma. Not these ones, just omega. The yellows you'll learn by the time you finish high school. Do I want you to use rho when you give me density solutions? You can use rho if you want, or you can use D. I really like the rho better. D is just, it's depth. Okay? But in any case, use whatever letter you prefer. So here are 2 examples. I give you a 200-gram object. It occupies 20 cubic centimeters. Calculate its density. You give me a formula. Then you write out your numbers with your units. No buck-naked numbers in science. and then you give me an answer with units. And the same here. Now, what's the difference between milliliters and grams? Well, one is how you measure solids, one is how you measure liquids. So grams per milliliter is totally acceptable for a liquid, where it's usually grams per cubic centimeter for solids. What's with this being less than 1? That's totally acceptable. If you worked out your rate of pay and you got 80 cents an hour, well, that freaking sucks, but $0.8 per hour is a perfectly valid number. Resist the urge to flip it and force this number to come out larger than 1. It's a very common thing students do. I recall wanting to do it myself. So 0.8 grams for every milliliter means that if I gave you a thimbleful of this stuff, it would not weigh as much as 1 gram. This would be a test question. This would be as big as it would get on a unit test in chemistry. A box has dimensions of length 10 centimeters, width 40 centimeters, height equals 2 meters. Its mass is 50 kilograms. Calculate its density. Now, notice the sneaky little trick in there. Do you see it? Do you see it? 10 centimeters, 40 centimeters, 2 meters. Uh-oh. Can we do that? No, we can't. But did I do this correctly? You wouldn't believe how many students would go 10 times 40 times 2. But think about it, 40 centimeters. Now, is this done proportionally? If this is 2 meters, does that look like 10 centimeters to you? Or is the diagram creating that cognitive dissonance where it's tricking you into believing something that isn't stated here? So what I've done down here is I've converted everything to meters. And then I got decimal 808 meters cubed. Okay, and now we get a density of this, 625 kilograms per cubic meter. Which makes sense. A cubic meter is about the size of my podium at school, if you remember that place. Maybe 2. So 625 kilograms in a cubic meter, that's not unheard of. A cubic meter is pretty large. I could cram like 7 or 8 bodies in a cubic meter. Well, forget I said that. Now here's an example. If I give you a box 12 centimeters by 27 centimeters by 10 centimeters, and it has a mass of 1.2 kilograms. So what is its density? Step 1, compute its volume. Give me that formula. It's not hard to do. And there we multiply it. I like putting things in brackets, square or round, doesn't matter. I've highlighted the numbers in blue for you, and notice I've kept the units. And I get this, 3240 cubic centimeters. Then when I calculate density, and I'm going to use rho. Row your boat. Density is mass over volume. There's my mass. There's my volume. I get a density of 0.37 grams per cubic centimeter. Ooh, and a mistake slid through. That should be an equal sign. Curses. It was so close to being beautiful. Now that we've calculated an example, what were you to do with this assignment? Well, let's say the one I just did was an example. So we calculated 0.37 grams per cubic centimeter. And if you look on this list of substances, the closest one is white pine at 0.4. So that's your answer. It's not going to be exact. You're talking the slightest mismeasurement, and it's wood. You don't think that's true for every white pine tree on planet Earth, or even every piece of the same tree. It's going to be very different. Even from the center of a tree to the edge, it's different. So you got to remember this value here. For water, it should be fairly close. But there are many kinds of steel. There's only one kind of mercury or carbon dioxide, but concrete, there's dozens of versions. So if you get a number like this, 0.37, and you don't see it exactly here, take the closest one you get, and that's good enough, okay? Now, I'm going to pause for a moment and let you see a video of me doing a hand version of the solution, which would be something you'd see on a test. Here's an example we can start off with that I'm going to use pen and paper here to help you get an idea of what you would be looking to do. When in doubt, locate all your measurements that are given. And by grade 12, they would expecting you, or grade 11, to do this. Itemizing them on the side never hurts. For many of you, it might be redundant. You already know, you spotted the measurements. And it doesn't matter which of these are the length, the width, and the depth. 12, 27 by 10. And the important thing is, there's no tricks here. These are all in centimeters. So your first step is going to be to calculate the volume. And again, we would prefer formula first. Then you're going to start with your numbers. And I'm going to give myself lots of room here. I'm going to bracket off the whole thing. And then I'm going to start putting in my numbers. 12, 27, and 10. And then we put pants on our numbers. Now this is just an illustration. I'm not interested in doing this to any exact degree. So you have to check with your other teachers on this. They may not be okay with this. I'm going to call that 10, and I'm going to call that 30. So in terms of straight numbers, that's 3, 0, 0, 0. I get an answer of 3,000. Now this is volume. A centimeter and a centimeter and a centimeter multiplied together. Let's just not change it from centimeters. Let's call it x. What do you get when you do x times x times x? Well, isn't that x cubed? So this will be centimeters cubed. You have measured on 3 sides. This is a volume. So you've done 27 by 10 by 12. It's a cubic measurement. Boxing it off for me is kind of nice. Draws it to my attention. For you guys, I'll even do this usually. And then you've got it clear. Now, that's not the whole calculation yet. We've got to go back and write out the formula now. Density equals mass over volume is equal to, and we know it's going to be, I was about to write 1.2 kilograms. We can't do that. Kilograms are not acceptable if we're using centimeters. We need to turn that into grams. Well, that's really easy. What's 1.2 kilometers? It's 1,200 meters. What's 1.2 grand? It's $1,200. Get my brush. It's 1,200 grams. We want grams per cubic centimeters, not kilograms per cubic centimeters. So I'm going to go in here, and the mass on the top is going to be in grams, and it's going to be divided by cubic centimeters. And to help you see, we have a mass of about 1,200 grams over 3,000 cubic centimeters. You can do this on your calculator, but come on, let's it's the same as 12 over 30. Okay, 12 and 3, common denominator, there are 10 threes, and there are 4 in here. So I'm getting an answer of 0.4. So my final answer seems to be a density of 0.4 grams per cubic centimeter. And that would be the hardest question I would ever ask you on a chemistry test. That's the limit of the mathematics we do in chemistry. But I want you to be able to do this one cold. I want you to be able to calculate that showing these steps, and I will also show it formally in full printing. But again, if you walk in and see this complete, it's harder to follow than when you watch the steps. So I want you to do your next example on your own using this series of steps. Calculating mass from volume and density. It's all well and good to compute density from data gathered in an experiment. However, centuries of men with no social lives whatsoever have populated volumes of books on the density of pretty much everything. In the daily world and in engineering, it's probably more likely you will calculate the mass from the density from one of these tables in these books put together by these men who had no life. For example, you might want to compute the weight of fuel aboard a rocket, or how much snow can load on the roof of the Sky Dome. When you go, we see 5 centimeters of snow today, how much is that actually putting as a load on the roof? Even rain on the Golden Gate Bridge will add a load weight. So density and volume can allow us to calculate these kind of things. So let's take a simple example. In movies, you frequently see someone pick up a large brick of gold. So I'm going to give you a block of gold that's 10 centimeters by 10 centimeters by 10 centimeters. This gives us a volume of 1,000 cubic centimeters. If we look at a single cube of 1 centimeter cubed, we can see that 10 by 10 by 10 means we have 1,000 of these. The total mass now is going to be the density of one part multiplied by the total number of parts in here. So mass will be density times volume. I put the density in blue because it is a characteristic physical property. It should be unique to the substance. This value here, the volume, we get to choose it. Hey, give me 1,000 scoops of gold there, and then you calculate the mass. But the density is something that you would look up in a book. So we take our two numbers, the density of gold, which is close to 20 times heavier than the same volume of water, and we multiply it by our 1,000 cubic centimeters. Please don't use your calculator. And you get 19,000 grams, which is 19 kilograms. Now, how big is a little 10 centimeter by 10 centimeter by 10 centimeter box? Well, for most of you, it's just a little bit bigger than you could cover with your hands, but it's not terribly big, right? Your hand is probably 10 centimeters long, so it's like a couple Rubik's Cubes. So it's got some serious weight to it in such a small, tiny space. Let's turn our example to a liquid and see what we'd get there. Hey there, everybody. This is the Disco King. I just got myself a new funky waterbed. Oh, yeah. It's 214 centimeters long, 150 centimeters wide, and 25 centimeters deep. How much is my bed gonna weigh? Well, we're gonna get our formula. Mass is density times volume. Oh yeah, I'm gonna multiply all these three numbers together, and I get 802,500 cubic centimeters of liquid motion in that bed. So my bed is gonna mass 1 gram per milliliter for water times 802,500 cubic centimeters. Excuse my mixing up of those units, but a milliliter and a cubic centimeter is the same. And this comes out too that my bed will weigh 802 kilograms. Heavy. See, that wasn't very hard. We just took the volume of his bed times 1 gram per cubic milliliter, and you got 800 kilograms in that water bed. Right? That's a ton, almost a ton. And I did not make up these numbers. I actually got them from a waterbed company. So yeah, that's a lot of weight to put on the floor. Right? If you consider most of the grade 9 kids are not up to 80 kilograms, you know, most of you are less than that. So we're talking like the weight of 10 people. So that's pretty heavy, man. Now, we can't all do everything in Disco Land. Cooter and Skeeter here, they're going to take a flea bath in their pickup truck. Now being rednecks, I'm going to assume it ain't a Toyota. It's some like ancient kind of thing here. So we'll just call it a Ford. Good old American Ford F-150, though. It seems a tad on the small side. And I looked it up, and a Ford F-150 has a 55 cubic foot bed volume, and the load capacity is 1 ton, or 1 tonne if you're French, but as I understand, a ton and a tonne are the same amount. So we want to know how close Cooter and Skeeter are to exceeding the weight limit of their Ford 150 pickup truck with their little old swimming pool flea bath in the back there. So first thing we're going to have to do is convert this 55 cubic feet into the metric system, or the System International. And I happen to know that 1 foot is about 30 of these centimeters, and so 1 cubic foot is going to be 30 by 30 by 30. So that's 27,000 cubic centimeters in a single cubic foot, and this is a 55. So I can't drive 55. Well, I multiply 55 by this, and I get 1,485,000 cubic centimeters, or about the volume of my Uncle Billy Bob's belly. Now, if you don't feel like doing the calculations by hand, well, you can just go on Google and type cubic foot, cubic centimeters, and I put in 55, and they gave me 1.55 million. You notice right down here, it said you can approximate it by multiplying by 28,317. So my approximation here was dang good. So anyway, I'm just going to split the difference, and I'm just going to say that the pickup truck is got about 1.5 million cubic centimeters in there. And again, I kind of like mix my units. Some teachers might object and say you should write water as 1 gram per cubic centimeter, but gol dong, it's the same thing. You know, it's a flea with a hat, flea without a hat, it's the same thing. So we multiply these two together, and I get out 1,500 kilograms, or 1.5 tons. So these boys shouldn't be like getting too much motion in the ocean going there, because it is right at the weight limit of that pickup truck. And that's if it's a new Ford 150. But you know, I've seen Dukes of Hazzards, and I know these vehicles can jump creeks and land on their nose and drive away. So I wouldn't be too upset about that. So I think these boys are within their safe limit. But man, where's their safety glasses? I don't know. Me in that head with the banjo. Man, he's got a metal ring.